NASA spent 25 years and $10 billion to launch the James Webb Telescope. Yet a new, superior project takes only 3. On the surface, the physics of that timeline don't seem to match the history. We have been pouring and polishing massive telescope mirrors for over a century. The manufacturing of the glass itself is a solved problem. The real bottleneck is the physical size of our rockets. You simply cannot fit a solid 40-foot mirror inside a payload fairing that is only 15 feet wide. To bypass this limit, engineers are forced to treat the mirror like a puzzle. They break the glass into individual hexagonal segments, all linked by thousands of specialized mechanical hinges. This allows a massive instrument to fold up tight enough to squeeze inside a standard rocket. This method introduces an extreme risk. Once the telescope reaches the vacuum of space, hundreds of individual motors must deploy in a perfectly timed sequence. If a single hinge catches or a motor fails by a fraction of a millimeter, there is no way to fix it. The entire multi-billion-dollar mission becomes a piece of orbiting space junk. Folding a mirror this way is a direct response to our launch vehicle limits. As long as our rockets remain narrow, the mirrors must become more complex, adding layers of mechanical vulnerability to every launch. The reason this new 3-year timeline is actually possible is because the most difficult parts of the telescope were finished years ago. The engineers didn't have to design the core hardware, they just had to find it. In 2012, the National Reconnaissance Office, the intelligence agency that manages America's spy satellites, contacted NASA with a strange offer. They had 2 fully constructed Hubble-class telescope chassis sitting in a warehouse, and they were willing to give them away for free. These telescopes share Hubble's 2.4-meter mirror, but their advanced optics capture a sky area 100 times larger. And there's a reason they were already built. While scientists looked at nebulas, the military spent decades using this exact power to look down at us. This means the next leap in our understanding of the universe was essentially paid for by the secret budgets of the Cold War and global reconnaissance. Even with pre-built military hardware, you still have to solve the origami problem. You need a way to get these massive monolithic mirrors into space without having to break them into pieces first. This is where SpaceX's Starship enters the story. It's a heavy lift platform providing the brute force capacity required to move industrial-scale components into orbit. Most legacy rockets are cramped, but Starship offers a 9-meter-wide payload bay. Instead of a fragile 18-segment puzzle, we can launch a monolithic mirror, one solid piece of glass, removing thousands of hinges. To visualize that scale, these mirrors are nearly as wide as the entire cockpit section of a Boeing 747. We are moving away from delicate laboratory instruments and toward the scale of heavy terrestrial machinery. Space engineering is moving away from high-stakes precision and toward a philosophy of building things heavy, huge, and relatively simple. But just as the path to heavy orbital industry becomes clear, a new challenge is appearing. For some tasks, we might not even need to be in space at all. A new generation of observatories is being built on remote mountaintops that can overcome the biggest problem with ground-based astronomy, atmospheric distortion. These facilities use adaptive optics. They fire high-powered lasers into the sky to create an artificial star, which computers use to measure exactly how the air is moving. They then warp their own mirrors thousands of times per second to cancel out that blur, giving them a view from the ground that is as sharp as a view from orbit. Combine these laser-guided telescopes with the repurposed military frames and the massive capacity of Starship, the landscape of astronomy changes. We are moving from a time of delicate, one-off scientific projects toward an era of volume-based construction. We are trading bespoke complexity for industrial scale. But if we are now capable of building heavy industrial megastructures in orbit, it leads to a much bigger problem. Where exactly are we going to get the millions of tons of raw materials that are required to build them?